Grade 11 Chemistry. This is video number 5. We are talking about covalent bonds today. Here's what we're going to talk about. First, we're going to review what covalent bonding is. Then we're going to talk about naming covalent molecules given their formula. And then we're going to draw some covalent structures. So not a lot of knowledge today, but a lot of thinking kind of stuff. So drawing structures is going to be an important part of the thinking part of our test, which is coming up pretty soon. So starting with covalent bonds review, essentially a covalent bond will occur between two nonmetals, usually. There are metals that actually do make covalent bonds between themselves, which is kind of interesting. These atoms will share their electrons with each other, so we say that they share. Essentially what's happening is the hydrogen will have a pull for outside electrons. We call that electronegativity. And this hydrogen also has a pull for outside electrons. We call that electronegativity. So they both pull on each other's electrons, and it ends up forming a new kind of electron shell that orbits both hydrogens at the same time. Some people like to think of it as like a figure eight around both molecules. You can think of it that way if you want. It's kind of helpful, but essentially they are now bound together because the electrons are going around both molecules at once, going around both atoms at once, and so they're stuck together with what we call a bond. This is where covalent comes from. Covalent, if you break it down, co means together, valent is that outside electron shell. So now they're both sharing this new thing that they've made, this covalent shell that is around both molecules. Which means that there's no ions, right? An ion means that one of the atoms will completely steal electrons from the other, but here this is not true. They're both seeing the electrons. And so this hydrogen sees 2 electrons, and this hydrogen sees 2 electrons. Both hydrogens are now happy. Both hydrogens are now stable. And they will remain like this. They will stay bonded like this. They're stuck together. We represent that with this line. That line represents the 2 electrons in the bond. That's how covalent bonds are formed. The big thing to remember is that no ions are formed, and that these are actually hooked into each other now. If we want to pull them apart, that's going to be a chemical change. There's going to be a bunch of energy that's either required or released, and it's a very strong, relatively speaking, bond. So that's covalent bond review. That was quick. Now we're going to get into naming covalent molecules given their formula. So I'll pause and set stuff up. When we want to name covalent bonds, or when we want to name covalent molecules, the thing to remember is that there's lots of different combinations and we can't easily predict the formula. The classic case that a lot of people know is carbon monoxide versus carbon dioxide. These are 2 different molecules and they have 2 different names. You probably know that carbon monoxide, is carbon monoxide is CO, and carbon dioxide is CO2. That's just one example of 2 different formulas. We're just carbon and oxygen. We can't really predict them because there are many different organizations of covalent bonds. They don't make ions, so we can't predict exactly how many of each thing any particular atom will bond to. So another example here would be, carbon can make this structure, methane. This is methane, which is CH4. That's one structure for that. Or it can potentially make this. All right, we could have carbons bonded to carbons, and this is propane, which is C3H8. And there's all kinds of other ones that can happen as well. So there's no way to properly predict what kind of formula we have. And that's why we have these rules that are based on the number of each atom in the molecule. Usually we put the central atom first, so if we go back to here with the methane, that's why I put CH4 because the C is in the center, or here for propane I put C3 because it's kind of central and the hydrogens are around the outside. So yeah, and what we literally do is just take the number, and we have these prefixes, and the prefixes are mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, and it does actually keep going past that. So there's like undeca, dodeca, stuff like that. You don't have to worry about that. Anything past deca, we're never going to have a molecule with more than 10. So just remember these 10. You have to remember these 10 prefixes. So what we're going to do is basically just try some. Right, here's a few that we can try, and I'm just going to use the comment feature here to type in the names. So Br2I4, right? Br2I4. We just need to look at our periodic table, figure out what Br is and what I is, and then we have to remember our prefixes. So Br2, that's bromine, and there's two of them. There's two bromines there. That's what the 2 means. So this is dibromine. And then just like in ionic compounds, we use an "ide" ending at the end of the second thing. That's just by convention. Dibromine tetraiodide. Right, tetra for 4. Tetra for 4 because there's 4 of them. Iodide because it's iodine. So dibromine tetraiodide would be the name of that formula. Here's P5F8. We have to remember what 5 is, and we have to remember what 8 is. 5 is penta, and then what is it? It's a P, which is phosphorus, pentaphosphorus, and then this is an F, and there's 8 of them, so 8 is octa, and F is fluorine, but it's the second element here, so it should be fluoride, pentaphosphorus octafluoride. NO5 is going to introduce some exceptions to the rule. When there's only one thing at the start, we don't write mono, just because of just to save space, basically. So think about carbon dioxide, right? There's 1 carbon and 2 oxygens, but we don't write monocarbon dioxide. We just write carbon dioxide. That's the easiest way that I can remember it in my head. So NO5, that would be nitrogen, right? We don't say mononitrogen, just nitrogen. And then 5 oxygens would theoretically be pentaoxide, right? Pentaoxide, because penta is for 5. But then there's this other little weird thing we do where pentaoxide is annoying to say and pentoxide is faster. So we typically say pentoxide. This is another thing that you can think of when you think about carbon dioxide and carbon monoxide. Monoxide, right? If we followed the rules properly, it would be monoxide, but that's annoying to say, so we just say monoxide, and it's just easier that way. Same kind of thing happens here with just 1 nitrogen, so this would just be nitrogen. And then there's 3 of these things. It's bromine again, but it's the second one. So this would be a tribromide, right? We need that "ide" ending because it's the second one, tribromide, and there's 3 bromines, tribromide. So these are typically very easy to name as long as you remember the prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Tetra is often the one that's hardest to remember for people. I always remember like a Tetra Pak, and it has 4 sides, but yeah. N2O5, we'll just finish this one, and I think that's enough practice for this kind of stuff. N2, 2 is di, there's 2 of them, dinitrogen. So dinitrogen and then 5 oxygens. Well, we've already seen that before. It's pentoxide. Pentoxide. It should be pentoxide, but we take away that A because it's faster to say pentoxide. Yeah, and there's a bunch of other practice here, but that's typically a relatively simple thing compared to ionic names. You just take it straight from the formula. Next up in our list is drawing covalent structures, which is going to be the bulk of this video. So when we draw covalent structures, we do stuff like this. We represent pairs of electrons that are bonding as lines, and sometimes there's lone pairs that stay on the molecule. We just represent them as a pair of dots like we normally do in a Lewis structure. And of course, Lewis structures will help us predict what kind of bonding these things are going to want to make. This methanol actually needs to have 2 dots as well 4 dots actually around it to show that there's a stable octet. So when we draw covalent structures, I'm going to go over to the whiteboard. Here's some more covalent structures that I've drawn. The trick here is we can use the table and our knowledge of Lewis structures, which is why we had practice drawing Lewis structures. These are the nonmetals. They're going to be making almost all of our covalent bonds. And we can predict how many bonds they want to make by where they are in the table and what kind of Lewis structures they have. So I'm going to draw a periodic table. I'm going to use this table and kind of give you guys some Lewis structures here. Carbon has 4 valence electrons, and so does silicon. It also has 4 valence electrons. Nitrogen, next to carbon, has 5 valence electrons. Phosphorus is under nitrogen. It also has 5 valence electrons. Oxygen is next to nitrogen. It has 6 valence electrons because we go up in electron number because we're going up in proton number across the table. Sulfur is under oxygen. It also has 6 valence electrons. Fluorine is our last one in the table here, before neon, but neon is, it's in the noble gases, so we're not even going to worry about that. Chlorine is under here with 7 valence electrons. Bromine, 7 valence electrons, and iodine also with 7 valence electrons. These are the main kind of suspects when we're talking about drawing structures. Typically, you won't see a lot of like selenium or arsenic or anything like that. It's really those guys. And I guess boron. Sometimes we'll get boron in a covalent structure, but it's relatively rare. And if you remember the rules in covalent structures, if you remember the rules, just like I'm getting an email, I'm going to pause. Okay, that's dealt with. So if you remember from Lewis structures, unpaired electrons are a key to how many bonds these things are going to want to make. So carbon has 4 unpaired electrons. 4 unpaired electrons. So it would want to share 4 electrons in order to make 4 bonds, so that it sees a full octet and is happy. Silicon also has 4 unpaired electrons. So it's also going to want to make 4 bonds. So we can make a general rule here that these guys are going to make 4 bonds. Nitrogen has 3 unpaired electrons. 3 unpaired electrons. So does phosphorus, 1, 2, 3 unpaired electrons. So they're going to make 3 bonds, and they'll have 1 lone pair. The 1 lone pair, that guy, is going to just stay together. They're okay. The lone pair is happy already. Oxygen, if you see the if you can sense the pattern here, this is oxygen and sulfur. They're going to make 2 bonds and 2 lone pairs. 2 bonds and 2 lone pairs. And fluorine, chlorine, bromine, and iodine all just want to share one electron, and they're going to make one bond, and they'll have 3 lone pairs in a typical structure. There are a few exceptions to this, notably phosphorus and sulfur. Because they are further down the table, they have less electronegativity. So on occasion, phosphorus and sulfur will actually make 5 bonds and 6 bonds respectively. Right? There's a little kind of asterisk here where this can actually make 5 bonds and this can actually make 6 bonds in some molecules. We especially see this when they're combined with oxygen or chlorine or fluorine, because the oxygen, chlorine, and fluorine are very, very electronegative. So we can watch out for that sometimes. If that does happen, I'll let you know, because it's an exception to the octet rule. So I'll be sure to let you guys know when phosphorus or sulfur are making more bonds than they should be making. Yeah, so we have this general rule across the table. This makes 4 bonds, 3 bonds, 2 bonds, 1 bond. Yeah, and that'll help us make structures, help us predict what kind of structures these things are going to make. You can also use the Lewis diagrams to actually predict these structures as well. So the next section here, I'm going to take a bunch of structures, and we're going to predict what kind of molecules these things are going to make. So I'm going to pause and set up some stuff. I've done my setup. We're going to start with the simple stuff and get into more complicated stuff. We're going to talk about predicting covalent structures. I've got my kind of little corner of the periodic table. Right? If you're ever confused, there it is. There's the corner of the table that I've followed here. CNOF, PSCl, bromine and iodine, and you just 4, 3, 2, 1. That's how many bonds these things are going to want to make. And then some general principles is that the atom that makes the most bonds will tend to be closer to the center, and that double and triple bonds are also possible. We're not going to start with anything with double and triple bonds. We're going to get into that a bit later. So let's start with our first one, which is a very simple one, CH4. When we write a structure, the one with the most bonds will tend to be closer to the center. I guess I should put hydrogen over here, right? Hydrogen, is just 1 bond. So CH4, we'll put the one with the most bonds closer to the center. In this case, that's the carbon. The carbon makes 4 bonds. So we'll put that in the center. We can actually draw this as a Lewis structure just to show off how Lewis structures can help us predict these things. So that's carbon, and then we have 4 hydrogens. We can put the hydrogens around the carbon, like so, and then we can make a bond, right? 2 electrons make a bond, so that's the structure. We can draw it as CH4, like that. That's the structure of CH4. We can do a few other ones like this. We can try, for example, H2O, the classic H2O. It means there's 2 hydrogens and 1 oxygen. Hydrogen makes a bond of 1, makes 1 bond. Oxygen makes 2 bonds, so more bonds closer to the center. We'll put the oxygen in the center. It makes 2 bonds. And there's the Lewis structure of oxygen, 6 valence electrons. And then we'll have hydrogens around it, and typically remember that unpaired electrons are the ones that are going to do bond order. So we'll put 1 there and 1 there. And then this gives us our prediction for what this structure is going to look like. Oxygen with 2 lone pairs and a hydrogen on each side, like that. So there's our H2O. We'll do something a little bit funkier. How about N2H4? This is called hydrazine. It's a rocket fuel, actually. So we look at our bond order. Hydrogen makes 1 bond. and nitrogen makes 3. This is actually a general rule that hydrogen is always going to be on the outside because it only makes 1 bond. Same with these guys. They're always going to be on the outside because they only make 1 bond. Once they make 1 bond, they're done. So it's very rare that they're going to be a central atom. So nitrogen makes 3. So we have 2 nitrogens. We have 2 nitrogens. 2 nitrogens and 4 hydrogens. We expect the nitrogens to be bonded to each other because otherwise the molecule isn't going to be a complete molecule. And then we have 4 hydrogens, so it'll look something like this. Like that. Oh, but the nitrogens don't see 8 electrons. 1, 2, 3, 4, 5, 6. Well, that's because they have that lone pair. We have to remember that they have that lone pair on them. You could also predict this with just straight Lewis structures if we want. So let's draw Lewis structures. Nitrogen, 1, 2, 3, 4, 5. Nitrogen, 1, 2, 3, 4, 5. And we can see here that this nitrogen can bond to this nitrogen, and then we have room for 2 hydrogens on each one. So that's hydrazine. That's hydrazine. Or, if you prefer, dinitrogen tetrahydride is how we would name it, with 2 nitrogens and 4 hydrogens. Hydrazine. Okay. Next up, we're going to talk about stuff where double and triple bonds are possible. Double and triple bonds are possible. So, let's think about something with a double bond. I'm going to put in, how about CO2? That's a good one, CO2. We have a carbon and 2 oxygens. Carbon makes 4 bonds. Carbon likes to make 4 bonds. Oxygen only likes to make 2. So we're going to put the carbon in the middle. It has 4 valence electrons. We can get that from the table. Oxygen, we can put an oxygen on each side, and each oxygen has 6 valence electrons. I'm going to draw them in a little bit of a different order than you might be used to seeing them, but the reason why is going to be abundantly clear very soon. So that's CO2, 1 carbon, 2 oxygens, CO2. And we can draw a line between each carbon and each oxygen, well, carbon and each oxygen, because the molecule has to stay together. But then, what's going to happen? The carbon isn't making all 4 bonds that it wants, and the oxygen isn't making both bonds that it wants. What's going to happen is we can make a second bond. We get a second share on this side, we make a second share on this side, and this is what's called a double bond. A double bond. When we draw them, we just draw them as 2 bonds like this, and then it's, we have the lone pairs there as well. Lone pairs. That's CO2. There's a few other interesting ones. Personal favorite, N2. Dinitrogen. This is the nitrogen that's in the air. It's 78% of what you're breathing right now. How can you just have 2 nitrogens when nitrogen wants to make 3 bonds? All we have access to is 2 nitrogens. Well, each nitrogen has 5 valence and wants to make 3 bonds. So nitrogen is going to make a triple bond to the other nitrogen. And then when we draw it, we draw it like this, where it's just a triple bond between the nitrogens. So that's N2. We have triple bonds. A few more. Let's just do a few more. Why not? Let's try an interesting carbon compound, C2H2. C2H2. We have 2 carbons and 2 hydrogens. So 2 carbons make 4 bonds. Hydrogens just make 1 bond. Carbon's going to be in the center. It's the one that has the most, what we call bond character. Each carbon has 4 valence electrons. They obviously have to bond to each other. That's 1. And then we have 2 hydrogens to put in here. Typically they'll go to the outside, so they can bond to the carbon like that. But then the carbons aren't happy. They're only making 2 bonds. So what's going to happen? I think it's pretty obvious. The carbons are going to triple bond to each other. So we have carbon, triple bond carbon, single bond to hydrogen, like that, and that is C2H2, aka acetylene. We can also have C2H4. C2H4, and same principle. Carbon goes in the center. It's got the highest bond order, 1, 2, 3, 4. It's carbon 1, 2, 3, 4. The carbons are going to bond to each other. And then we have to put 4 hydrogens. You can probably predict that it's going to be 2 hydrogens on each side. All right, each hydrogen has 1 valence. So there we go, like that. And then these carbons are only making 3 bonds. They want to make 4. They want to make 4 bonds. So like that. Maybe draw it a little bit nicer. Right, spread it out a little bit. That is C2H4. C2H4, like that. C2H4. And we can also have C2H6. C2H6. Which, 2 carbons. Each carbon has 4 valence electrons. It wants to make 4 bonds. It'll bond with itself. We have 6 hydrogens to spread out, and we have 6 spots. 1, 2, 3, 4, 5, 6. So, kind of obvious. The carbons are single bonded, and there's 6 hydrogens just spreading out. That's ethane. And that would be how you draw the structure of ethane. So here we've got C2H4, C2H2, and C2H6, all just carbons and hydrogens, all of them just binary. Then we can name these. They'll have different names. This one is dicarbon dihydride, because that's how we name them, right? Carbon is the first, and then dihydride, 2 hydrogens, dihydride. This one here is a dicarbon, because they're all dicarbons, dicarbon, and H6. So let's think for a second, what would H6 be? Hexahydride. Hexahydride. And C2H4 is going to be, again, dicarbon, and tetra for 4, hydride, dicarbon tetrahydride. And those are some molecular structures. You can get into some very, very interesting ones. You can have more than just 2 elements, but there's going to be a worksheet for that, so look out for that worksheet and try it out, and we'll take it up in class today. So yeah, that's it. Hope you enjoyed it, and thank you very much.